Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 103 Waves and Oscillations. Today, it is the ninth lecture of this course, and the topic is force oscillations and resonance. First, I will give the learning objectives. At the end of this presentation, the student will know what is meant by force harmonic oscillator. Also, they will be able to distinguish between the natural frequency omega and the driving frequency omega d for a force harmonic oscillator. Also, they will be able to understand the resonance that will occur when the driving frequency matches the natural frequency of the oscillator. In this course, we are following the book Fundamentals of Physics by Holliday, Resnick and Walker, 10th edition. Some of the figures in this presentation is taken from this book. First, we want to see how the descriptions of a simple harmonic oscillator be converted to a force oscillation. So in this course, first we have discussed free oscillations such that the oscillator oscillates for all time uh, without having any dissipative mechanism or resistive forces that will damp the oscillation. After that, we have discussed damped oscillation, where we have taken the same oscillations, but uh, then we have to consider the resistive forces that will appear due to the presence of the medium. So in the equation of motion, the opposing force will give rise to damp the oscillation. Now the free oscillations can be converted to force oscillations if a periodic force exists such that the oscillations of the oscillator will grow if again, like the free oscillator, we don't have any resistor force. Similarly, one can have a force damped oscillator, or in another word, the most common name is the driven damped oscillator, where there exists a periodic force, constant periodic force, but there is also a dissipative mechanism through which the oscillation will damp due to the resistive forces. So in this lecture, we will be discussing a force oscillator where the damping mechanism is also there. So for that, we need to consider the oscillator that we have discussed in our previous lecture. Now this is a damped harmonic oscillator where we have a block of mass m that is attached to a spring of spring constant k. When this block oscillates, uh, the oscillation will damp after some time because of this portion, that is, this block is connected to a massless rod, and that is connected to a vane that is placed inside a liquid medium having a damping constant p. Now for a force oscillation, we need to modify this figure a little, but before doing that we need to bring the measurement tool. That is, we have a coordinate system. in which we can measure the oscillation along this x direction. Now at x is equal to 0, that is at this position, this oscillator is in equilibrium. Now to modify this damp harmonic oscillator uh, so that it converts to a force oscillator, for that we need to consider another massless rod, so that one can apply that constant periodic force. Now with the help of this constant periodic force, the amplitude of the oscillation will either increase or it will remain constant, since we have a dissipative mechanism as well. So in the force oscillator, we have an oscillatory driving force that is applied to the damp oscillator. The magnitude of that force is F naught cos of omega d t plus phi prime, where this F is the magnitude of the force and that force is harmonic in nature with a frequency omega d. Now, as I told you, our observation will be that the amplitude of this oscillator, which oscillates along this positive x direction and also towards the negative x direction, the amplitude or the maximum displacement along this coordinate will either grow because of this force or remains constant because of this mechanism, the damping mechanism. So if the energy imparting per oscillation exceeds to the energy lost from the damping, or in that situation we can say that the amplitude may grow or remains constant if the energy imparting per oscillation exceeds or exactly matches to the energy loss from the damping. That is, if the energy which this oscillator receives with the help of this force, if that is greater compared to the energy lost from this oscillator with the help of this mechanism, so then the oscillator amplitude will enhance, and similarly if the two energies such that the energy received by this oscillator from this portion is equal to the energy lost by this oscillator by this mechanism, if the two are equal, then the oscillator will uh, oscillate with constant amplitude, and that will be the steady state solution. So under steady state condition, that is the two energies, that is the energy supplied by this force is equal to the energy lost by this mechanism. If the two are equal, then that is the steady state condition. So the under the steady state condition, the oscillation will continue with constant amplitude, and the oscillator will now be oscillating with the driving frequency omega. Now in this lecture we will see the mathematical descriptions of this force oscillator under the steady state condition. So for that we need to identify the forces which are acting on this block. The first one is the damping force, as we have discussed in our previous lecture, that this damping force arises because of the motion of this vane inside the liquid which is connected to this block. So that damping force is proportional to the velocity of the vane inside this liquid, and this negative sign shows that this force, this damping force, will oppose the motion of this block where B is the damping constant. The second force which is there acting on this block is the restoring force. Fs is equal to minus kx. Now, as we have discussed previously, that this force tries to restore the equilibrium. For example, this is the equilibrium position. So when this block starts oscillations, so this restoring force will try to restore the equilibrium. So that's why there is a negative sign. This k is the spring constant. Now, since we are uh, having a third force, because we are discussing the force oscillation, so we have another force, that is Fd, whose magnitude is F naught cos of omega dt plus phi prime. As previously, we have ignored the gravitational force just to make the mathematical equation, the equation of motion, straightforward. So we had to ignore the magnitude of the gravitational force on the block, assumed to be very small compared to these three forces. So the equation of motion under this condition will be ma, the net force, is equal to minus bv, the damping force, then minus kx, the restoring force, and then we have the driving force which is acting, due to which this damp oscillator is now force oscillator. Now this one is the force oscillator, for which we have discussed this equation of motion. Now this equation of motion can be solved to obtain the solution that will describe the oscillations of this oscillator. So first we need to rearrange this equation. That is, we need to move these two terms on the left hand side, so that we have ma, we have plus bv and plus kx, and then equal to the force term. Similarly, we had to divide m across the equation, and then one can write this a as d square x over dt square, and also this v as dx over dt, and then the force term, the m will appear across all the equation, and it will be equal to 1 in the first term. Now this equation can be solved to obtain a solution under the steady state. We will discuss this solution, or this equation. This is an inhomogeneous second order equation. The solution is a complex solution. We will see the solution on the next slide. But under steady state condition, one can obtain this equation, the solution. First, we will discuss the outcomes of this solution, and then we will discuss the solution on the next slide. So, if one compare this solution with the ideal oscillation, that is having no damping term and also having no force term, that is, if one remove this portion from the oscillator and also this portion from the oscillator, and then this will be oscillating freely. So in that situation, we obtain x of t equal to xm cos of omega t plus phi. So it was similar to this kind of equation, but if you see, we are having a damping term and also a force term, but under steady state condition, this give us a similar solution to the one we have discussed for the free oscillator. But in that situation, we have the omega t, omega being the natural frequency of the oscillator, that was having a magnitude under the root K over M, and Xm was the amplitude of uh, the oscillator. But now this A is different than that Xm because of the uh, resistive term, the resistive force, and also the periodic force. So this A is the amplitude of this force oscillator that is proportional to the magnitude of the force F naught, and also it is proportional to the difference of the frequencies, that is the driving frequency at which this driving force is acting, and also omega naught. This omega naught is the natural frequency of this spring mass system. Omega naught is equal to under the root k over m, while omega d is the frequency of this uh, uh, force which is applied here, and also this a is proportional to the damping parameter b. So here if one ignores this b, that is if b is equal to 0, that is this damping mechanism is not there, so that will be just a force oscillator where we don't have any damping mechanism. So in that situation this b will not be, this term will not be there. Now if we uh, look at the amplitude of this force oscillator uh, by uh, by plotting the omega d over omega versus the amplitude. So at omega d over omega equals to 1, that is when the driving frequency is equal to the natural frequency, this in this figure this should be omega naught, right? We have used omega naught for the natural frequency, but in your course book it is as omega. So if the driving frequency is equal to the natural frequency of the oscillator, such that these are almost, the ratio is almost 1 and their difference is 0, that resonance point. uh, in physics, resonance describes the phenomena of increased amplitude uh, that occur when the frequency of the periodically applied force is equal to or very close to the natural frequency of the oscillator. So if these two frequencies are equal, so this term will be 0, and we will be left with this B factor, which is the damping factor. So one can see here from these three different plots that uh, least damping is B is equal to 50. So for B is equal to 50, this the denominator in the amplitude term is small, so that this A will be large. So for the time being, if we ignore this portion and we are having omega d equal to omega and this b is equal to 0, so this denominator will be assume that it is very small, almost equal to 0. So in that situation, this amplitude, this A, and hence this amplitude will just blow up due to the resonance, because the driving frequency is equal to the natural frequency of the oscillator. But if one keeps this damping portion, so that we have a non-zero B, so in that situation the amplitude will be largest for situation where B is the least. So now we will be discussing the solutions. So this one is the equation of motion for a forced harmonic oscillator that we have rearranged to this form. Now this equation is a second order inhomogeneous differential equation, and the general solution is having two parts. The first one is the complementary part, the complementary function. Uh, that function, that actually that part of the solution uh, is only when we make this right hand side equal to 0. That is, by making this differential equation uh, similar to the one we obtained for damped harmonic oscillator. That is, this force term is equal to 0 and we have only the k over m term and we have a damping term. So in that situation, when this right hand side equals to 0, and then if you remember, we obtain the solution for a damped harmonic oscillator, x of t equal to xm, the exponential term, and also the harmonic part, if you remember. Now this solution we obtained for a damped harmonic oscillator uh, under the first case, that was the uh, lightly damped situation, that is, the damping is small, uh, so that the solution still remains oscillatory. Now the second part of the solution, the equation of motion for the damped oscillator, is having this x of p, which is uh, known as a particular solution under the steady state, and that we have discussed on the previous slide. So this equation is having two parts of the solution. One is the complementary part that exists once we have this equals 0, and the other one is the particular solution under the steady state, uh, which we have discussed on the previous slide. Now, where we have discussed this A, that is proportional to the magnitude F of the periodic force, and also it depends on the difference of the driving frequency and the natural frequency, and of course it also depends upon the damping factor. But in my last lecture I told you that this x goes to 0 for large time. That is, the solution for a damped oscillator, the x goes to 0 once we have large time. That is, for large t, this exponential will eventually make this x 0. So the general solution of this forced oscillator equation will then be we will be having this part, because for large time this goes to 0. Now these solutions are discussed in this classical dynamics book by Thornton and Marian, and this discussion and the solution of the differential equation, complete solution, is given in chapter 3, Oscillations. Now the students of PHY 103 need to just adopt this solution without going into the complex derivation, which is not required. You will study that in your classical mechanics book course, sorry. And with this, I thank you for your time.